So hello everyone and welcome to this new course that we are starting from today, Design and Detailing of RCC Tall Buildings. And this is our session 1. So before I begin, we would like to thank you all for joining this course, and you have given a great uh, feedback and appreciation on this course by joining in large numbers. And many of the participants are joining an Oxen course for the first time. So welcome. Many of the participants are our regular participants and they join almost all our courses. So thank you to them also. And many of you are joining after a gap of 1 or 2 years. So welcome back. So this new course that we are starting is Design and Detailing of RCC Tall Buildings. Is my voice audible to everyone? Yeah, I hope my voice is audible. So those who are old participants, they know, but for the new ones, I'll just say that you will be kept on mute and your video will be also switched off. So the way to communicate with us during the session will be to type into the chat box, and we regularly monitor the chat box. So whatever your question, query, doubt, difficulty, you can just type in into the chat box. Okay. And we will quickly reply to you. So let us start then. And I'll just, you are able to see the screen also, right? I am sharing one PPT today. So generally we will not be having PPTs during our course, but in session 1, I like to show you a few things. So we are going to present a small presentation. Is this screen also visible? PPT? Yeah. So very quickly, we'll just quickly discuss what are tall buildings. Some of these things will be a repeat from our introductory session. We had discussed a few things in the introductory session as well, but it's important that we discuss it once again over here. So what are tall buildings? How are tall buildings different from your regular buildings? What is the scenario in India right now? And why this course? Why are we doing this course? Why have you joined this course? A few details about this course, and then we will come to the historical development of tall buildings over the past, let's say 100-120 years. Okay, so this is going to be the brief agenda for today. So what are tall buildings? So this term tall buildings, as you can see, is a relative term. I had given this example earlier also. So for example, my height is, let's say my height is 5 feet 6 inches. Okay. So if I am standing at 5 feet 6 inches, if I am standing in a crowd of people who are having, let's say, 5 feet height, or if I am standing in a crowd of young kids, then I look tall, isn't it? Hello. I look tall if I'm standing amongst, let's say, young kids 3 or 4 years old, then I will look very tall, isn't it? But then if I come to a gathering where people are, let's say 6 feet height, then I will not look tall. I hope you get it. So this tall, short, this is a relative term. It's not an absolute term, so to say. So, so for example, if I talk it in terms of building, if you have a 20-story building, okay, if you have a 20-story building, let's say in a city like maybe a tier 2 or a tier 3 city like Indore, maybe. Okay. So in a tier 2, tier 3 city like Indore, even a 20-story building will be considered as a tall building. Correct. So for example, in our city, to give you a practical example, in our city as well, the tallest building that we have, tallest habitable building that we have is a 20-story tall building. So even a 20-story building will be tall for us. But if you, let's say, go to New York, Manhattan, or if you go to Dubai maybe, or if you go to Shanghai, even a 50-story building may not be tall enough because there are 100-story, 120-story buildings, 80-story buildings all around. So this term tall, when I say, it's a relative term. It's always to be understood in terms of the environment where you are. Okay. So then this definition as per height may not be a good definition to call a building tall or short. This is one thing that I want you to understand. Now, if this is not a good definition, another way of looking at tall buildings will be, and another way will be the proportioning. Okay. What do I mean by proportioning? So, for example, uh, if I have a building which has dimensions having a taller height and a shorter plan width. Okay. So this may look tall compared to a building which is squat like this, isn't it? So compared to a building which is quite squat, squat means which has a greater width and substantial width as compared to height. Now this building which is slender, when I say slender, I mean which has a higher length to width ratio, height to width ratio. This may look slender. This may look this may look like a squat building. So if a person is standing, let's say, he or she may feel that a slender building looks taller, isn't it? A slender building may look taller as compared to a squat building. So it also depends on proportioning. The overall proportioning of your structure may also give the feeling, may also give this visual feeling of shortness or tallness. Is this clear? I hope my voice is audible. Hello. Yes, no. Voice is audible? Yeah. So it may also depend on the relative proportioning. So now this is also not a good definition of calling a building tall or short. Another way to look at whether to call a building tall or short may be if we are using any special systems or any special external systems are being used in the structure, then we might like to call it as tall. For example, you might have heard or seen or read that in some tall buildings, we may have to use some additional damping like structures. Okay. We may have to use additional damping like structures in some tall buildings. I think you may have heard of Taipei 101, or you may have heard. So Taipei 101 is one of the earliest buildings which used a tuned mass damper to control the lateral deflections and accelerations. So whether or not any special such system is being used to control damping or to provide additional damping to the system may decide or may help us in defining whether a building is tall enough or not. Okay, so this can be one of the other way to look and say that whether your building is tall or short. But usually neither of these three or four definitions or neither of these three classifications are used as such. The classification or the parameter on which we generally like to call a building tall is that when lateral loads begin to dominate. So if your lateral loads like seismic or wind, if they begin to dominate the design, the serviceability design, the strength design of your building, then usually we like to call our building as tall. Is that clear? So neither of these three definitions that or neither of these three classifications that I just said, we will use as such, but we will be sticking to this classification that we will like to call a building as tall when the lateral loads begin to dominate the design and the sizing of the system or the structure. Okay. So lateral loads will dominate not only the strength design, but they will also dominate the serviceability design. When this begins to happen, then we start calling that, yes, this building is tall enough. Is that clear? So this is the general way in which we will like to look at tall buildings. Mr. Chenmai is saying in G+10 building, the lateral loads are dominant loads. So can we say that building is tall? In G+10, generally, if you see the general plan size, if it's not very slender means if you look at the width of a G+10 and if you compare it with the overall height, the lateral loads, yes, we design for lateral loads, but lateral loads, when I say dominate, I'll like to explain what I mean by dominate. When I say dominate, the thing that I want to say is that whether they are adding to the cost of the building. Okay, so if lateral load in shorter structures, they are not adding to the overall cost. I mean, what I am trying to say is that if you are having, let's say, a G+10, okay, you had to provide the gravity system. You had to provide the gravity system. So you have provided your columns, walls, shear walls, whatever. Now, this system that you have provided to take gravity loads, this itself is more or less sufficient to take the lateral load also. Maybe you have to increase slightly the reinforcement percentage, or maybe you have to put slightly more size to it. But overall, just a 3-4% increase, and you are good to take the lateral loads also. So then I will not say that lateral loads are dominating as such. Yes, we are designing for lateral loads. Yes, lateral loads are adding to the overall cost of your structure, but they are not a major component of the overall cost. So when I say dominate, the design, the strength design, the serviceability design, the drifts, the deflections, the accelerations, all those have to be dominated, or all those have to be controlled by lateral loads. Usually then we would like to call that yes, this building is tall. Generally in G+10, as I just said, your height and the aspect ratio or the plan size may not be such that lateral loads are dominating the overall design. We will design for lateral loads. The lateral loads will add to the cost also, but it's not going to be a very steep cost that lateral loads will incur. Okay. So usually when lateral loads begin to dominate, lateral loads begin to affect your strength and serviceability design, then we usually call our building as a tall building. If you look at the Council of Tall Buildings and Urban Habitat, CTBUH, it calls any building, let's say up to 300 meter as tall. Any building means, of course, lateral loads are dominating, and up to 300 meters, it calls them as tall buildings. 300 above, it calls them as super tall building, and more than 600, it calls them as mega tall buildings. Okay, so this is a uh, sort of classification that has been put forth by CTBUH, and I'll recommend all of you to visit their website. There are some very good resources that are available on their website, so you must have a look at them, and they will help you to understand a lot of things, and they will teach you a lot. So must visit. Okay. So from this slide, what I want you to understand that there is no particular definition for tall buildings as such. The only one takeaway that you can have is that if you have to think uh, more about lateral loads in your design, and if your lateral loads are affecting your design in terms of strength and serviceability, then we will call them as tall buildings. So how are they different? That's what I was telling you in the earlier slide also. So because tall buildings are governed by lateral loads, the overall proportioning of your system, the load resisting system planning for gravity loads, for lateral loads, the planning of foundation, substructural system, all these have to be thought in a different manner than a regular building. Okay. See, if you can design a beam for, if I ask you if you can design a beam for bending moment of 100 kilonewton meter, all right, will you be able to design another beam for 600 kilonewton meter? Yes or no? What do you think? Or if I ask you if you are designing a column, if you are designing a column for, let's say, an axial load of 2000 kilonewton, will you be able to design another column for, let's say, an axial load of 20,000 kilonewton? What do you say? Yes or no? Hello, quick. I think so. You will be able to design, isn't it? If you know the basic process, if you know the basic process, there is nothing that stops you from not being able to design, isn't it? So then, what is the difference? What is the difference? Let's say in a tall building which has 40, 50 floors, maybe the column loads are 20,000 kilonewton. If you are having a G plus 2, G plus 3, maybe the axial load is 2000 kilonewton. If you're able to design your columns for 2000, obviously you can design them for 20,000 also. So then how is the design of tall buildings different from a regular building? So that's what I'm trying to explain, that when it comes to tall buildings, because lateral loads are governing, you may have to come up with some different structural systems. You may have to come up with, or you may have to do some special analysis. You may have to carry out some special analysis to take care of some specific effects that are seen in tall buildings. You may have to think in a different manner about the substructural system, isn't it? So for example, if a G for a G plus 10, maybe you could have done a simple raft and things would have been safe for you. But if you are doing a G plus 60, the loads are so high and the strata is not that great that you can support a G plus 60. So maybe you have to do pile plus raft. So you have to come up with a different structural system for it. Okay. So in this manner, the design, the analysis may be different when it comes to a tall building. Also, when we are doing normal structures, which are not very tall, let's say G plus 4, G plus 5, G plus 10, we usually think only in terms of strength, isn't it? That means we provide our column sizes, we provide the column reinforcement, we design the beam sizes, beam reinforcement, slab sizes, only in terms of strength. Clear? But when it comes to a tall building, not only strength, not only strength, but you may also have to think about the stiffness or flexibility. What does that mean? This means that you may have a case where your system is strong. The strength is there to take the loads, but it's not stiff enough and it's deforming so much. Okay. So it is strong enough, but it is not stiff enough. So if it's not stiff enough, you may not be able to allow such proportioning, or you may not be able to allow such sizes. Just to give you an example, if you see, let's say, what example should I give? I don't know if you have seen eucalyptus trees, or have you seen eucalyptus trees? Or maybe a bamboo forest. So under the effects of very heavy winds, have you seen what happens? The eucalyptus trees deform a lot. I don't know if you have seen it or not. Hello. They deform a lot. They undergo very heavy deformations, lateral deformations. Have you seen this thing? Or even a bamboo forest, if you observe, even if there's a standalone bamboo tree or any such thin, small tree, if you notice, it will deform a lot. But is it falling down? It's not falling down. That means strength is there. It has the strength. It's not falling down. But the problem is of stiffness. Okay. Stiffness is a problem. And because stiffness is a problem, it's not able to control its deformation and it's deforming a lot. So that's what I mean by strength and stiffness. Usually in shorter structures, strength is the sole criteria which we think about, and we don't think much about the stiffness and flexibility. But when it comes to tall building, sometimes our sizing and our proportioning may be decided by the stiffness criteria. Is that clear? What I mean to say is that, let's say in a tall building, maybe a column size of 1200 by 1200, just to give you an example, just some hypothetical figures. Maybe a 1200 by 1200 size was sufficient with respect to the strength criteria. Okay. But this size, even if I was maintaining this size in the column, the deformation was very high. So what did I had to do? I had to increase the column size to, let's say, 1400 by 1400. Okay. The beam size over here, strength wise, let's say a beam of 400 by 600 was sufficient. Just giving you random figures. Okay. This was sufficient strength wise. But because I had to control the lateral deformations, because I had to control the lateral accelerations, maybe I had to deliberately increase my beam to 500 by 800. Are you getting this point? So that's what I mean when I say that the flexibility and stiffness may take precedence over the strength design. So here when I'm providing these sizes, when I'm providing a 500 cross 800 size, or when I'm providing this column size of 1400 by 1400, it's not governed by strength, but this is governed by stiffness criteria. So in tall buildings, we may come across such situations where we may have to think on these terms, that our structure must be provided with adequate flexibility, stiffness, etc. Is that clear? So in this manner, again, a tall building design may be different from a regular building design. Clear? Is this making sense? Quick yes, no? Very good. Then another way in which we may have to look at tall buildings are the dynamic effects. So we just not have to think about the lateral loads, but in lateral loads, we may also have to think about the time varying component of it and how it may affect your structure. A good example of that is your wind loads. So when wind loads hit on your tall buildings, wind load generally have a static wind load. Static means there is a steady state component of your wind. Clear? Hello. There is a steady state component of your wind, which means that, let's say, a wind is flowing steady state, constant speed over a large period of time. It's called as the steady state component. But in your wind, there is also a transient component which varies with time. There can be a transient component of your wind, or what we can also call as the gusting wind. Hello. Gusting wind means a wind event which will last for, let's say, a very short 2, 3, or 4 seconds, and which will have a higher speed than your steady state wind. Have you ever felt like that? Gust winds. In Hindi, we call it as hawa ka jhoka. Okay. I don't know if you have felt that hawa ka jhoka, which comes, let's say, for a very small time interval, 2, 3 seconds. Nobody has felt hawa ka jhoka. Yeah, people have felt. Good. So this gusting wind, which may last for, let's say, 2, 3 seconds, how does it become important for our tall building? It becomes important for our tall buildings because our tall buildings may have the fundamental time period, or may have the natural time period in this region. What I mean to say is that if my building time period is also in a similar range, let's say, okay, if my building time period is also in this range, then this gusting wind may cause what? This gusting wind may cause what? Hello. I'm saying this gusting wind may have a duration of, let's say, 2, 3, 4 seconds. And if my building time period is also of a similar magnitude, let's say my building fundamental time period of vibration is also in the similar bracket, then this may cause, yes, what Mr. Mehul and Mr. Jay are saying, it may cause resonance. Okay. And due to this resonance, what may happen? There will be an increased, response, or what we can call as amplification of response. Are you able to get this? Hello? Yes or no? Yes. So that's what I mean when I say that dynamic effects of lateral loads also become very important. Now, why are dynamic effects not important in a smaller structure like a G plus 10? So if I have a G plus 10, okay, if I have a G plus 10, what will be my usual time period? Let's say a G plus 10 building will be how much? A G plus 10 will be how much tall? Let's say uh, 3 meters for each floor level. So around 30 meters. Okay, 33 meters. So tell me what will be an approximate time period of this? Usually for time period, you may use this formula zero point 0.1 into n. Okay. Usually you can use this formula 0.1 into n. If you look at the Japanese code, I think it has a formula of h over 50. Simple formula they have given. A good formula can be 0.1 into n. So n are number of stories. So for example, just very rough formula, 0.1 into n are 10 stories. So around 1 second will be the time period. Okay. So this is 1 second is the time period. My gusting wind is having a 3 or 4 second duration. So this gusting wind will not have a resonance effect on my G plus 10 structure. Is it making sense? Hello. What I'm saying, if I have a G plus 10 structure, my gusting wind may not have a response on my G plus 10 structure because the time periods are not matching. That means the fundamental time period of my building is not in sync with the gusting wind duration. If I take a taller building, let's say 50-story building or 40-story building, okay, a 40-story building may have a time period of how much? A 40-story building may have a time period of around 3 or 4 or 5 seconds. Now here the problem may start occurring that my gusting wind, my gusting wind time period and my building time period are coming close to each other, and this may cause amplification of responses. Is that clear? So not only steady state wind, but we may also have to think about the transient component of wind. And that is what I mean that dynamic effects may become important. I hope this point is made clear. Now, why I'm not taking seismic in this? Because seismic is usually always a dynamic load, which is a inertial load changing with time. So I'm not considering seismic much over here. I'm focusing more on wind because wind has these two components together, steady state as well as the transient component. So therefore, I spoke more about the wind in this case. I hope this is clear. So in this manner, again, the design of tall buildings can be considered to be different from a regular building. What are we discussing? Please remember, I'm just trying to explain how a tall building design may vary from a regular building analysis and design. Okay. How a tall building analysis design may vary from a regular building analysis and design. That's what we are trying to discuss. Now, this is not very uh, important differentiation. But yeah, we may have to come up with materials of greater strength. So it's common to see, let's say M60, 70, 80 high grade concretes being used. It's common to see high strength steel being used. It's common to see composite systems being used in tall buildings. The reason being that the loads are so high, and to control the sizes, to not have very large sections, because obviously large sections means less usable space. So obviously we would like to have materials used of greater strength, right? So this can be another way in which a tall building can be thought to be different from a regular building, though not very important. And tall buildings, you may have to think about some innovative and different construction techniques. For example, you may have to think about slip form techniques. You may have to come up with slip forming solutions where you do continuous concreting, continuous casting to save on time. You may have to come up with some different systems which save your time and help you in faster construction. So in tall buildings, these issues may also be need to thought about. And one just on the side, many of one just difference I just thought I'll tell you. Many of our structural engineers have this complaint that the contractors are able to do G+5, G+6. They only do themselves, isn't it? They don't even take the drawings from structural engineers, and a G+5, G+6, they will only do on their own. They will provide normal sizes. They will provide a 16 dia, 20 dia bars. They will provide your usual beams. And for G+5, G+6, nobody is coming to the structural engineer. I have seen many structural engineers having a complaint about this. So maybe if it comes to G+40, G+50, contractor would not like to design on their own, isn't it? Design means they will at least have to come to a structural engineer to take drawings design from a qualified engineer. So maybe this can be another difference, that contractor built buildings may not be possible when it comes to taller buildings like 40-story, 50-story tall, isn't it? So that's a good news for us. If in future such type of buildings are built more and more, you may not see contractor directly going on site and without consulting structural engineers building anything that he or she feels suitable. So that is a good thing. That's a good difference for the structural engineers. Anyway, so uh, what is the scenario in India? I had discussed this earlier also. So very quickly, I'll just take you through it. And we will then discuss more about this in the historical development of tall buildings. So in India right now, if you see, more and more tall buildings are being built. When I say tall, it's mostly around the, what's the usual height that you're seeing in Indian cities these days for tall buildings? What's the usual height that you're seeing? So the usual height that you're seeing these days is what? Around 50, 60 stories, 50 stories, 60 stories. Yeah. So usually you are seeing these 50, 60 stories being built more and more. And their height will be in the tune of around 200 meters. Okay. Their height will be in the tune of 200 meters. Beyond this, if you see in the Indian context at least, people are not able to people are not able to derive economic value of constructing taller buildings than this. Are you getting this point? So if you try and go beyond, let's say 225, if you try and go beyond 230, the delta, that means the benefit that you will get from adding more floors. Okay. The benefit that you may get from adding more floors is not as much as the cost that you are requiring to input in building taller. So it may not make economic sense beyond the point to go tall and tall. Is that clear? So in India right now, the situation is that people are more comfortable building in this range of 200 to 225 meters at max. This means around 60, 70 stories, assuming 3 meter for each story, and a few stories which will be non-usable stories, which will be used for mechanical spaces or some MEP spaces. So those are dead stories for us in terms of habitation. So when I say 50 stories, there will be 4 or 5 mechanical stories which will be unhabitated. So roughly speaking, around 200 to 25 meters is the level of tallness that we see in the Indian context right now. Is that clear? So this is what is happening. And in the last 5-10 years, mostly post-pandemic, there has been a upsurge in the buildings, in the taller buildings being built. Mainly the focus is more in the region in Mumbai, Pune, Bengaluru, Hyderabad, not so much in NCR, but yes, buildings are being built. Mostly these are residential buildings, residential apartment buildings. A few of them are commercial also, but mostly they are residential buildings, multi-tower buildings, apartment buildings that you see are being done. And the material of reference is mostly RCC. You don't see a lot of composites also. Structural steel is also not seen as such. Mostly the material of choice is RCC. Is that clear? I mean, this is the scenario as of now. It may change. Who knows, after 5-10 years, this trend may change and we may go on building taller and taller. But right now, this is what is happening. See, you must keep this thing in mind that tall buildings may not always be economically viable for you. All right. So, I mean, yeah, keep aside the ego of the developer in building a tall building. But at the end of the day, if it's not economic, if it's not making economic sense to the developer, they are bound to lose money on it, isn't it? If your tall building remains unoccupied, you are going to lose a lot of money on it. I had given this example earlier also. Burj Khalifa, if you see, it's not fully occupied. Okay, the Burj Khalifa, which is the tallest building in the world right now, it's not fully occupied. It's not making money as such. Obviously, the city of Dubai, the Emirate of Dubai makes money. The Burj Khalifa has now been recognized as a major tourist attraction. So because of tourism, it may make money, but out of real estate, it's not making so much money. Okay. So you have to be very careful when it comes to going tall because it may not always make economic sense. So the economics of a tall building, you need to study into, you need to study in depth and only then take up such projects. Many of the tall building projects get stalled, they remain incomplete because uh, the developer runs out of money or the developer finds that this project may no longer be viable. So they have to either cut down on the height or they have to sort of abandon the project. In China, if you see, I was reading, in China, they have now put a upper limit and they are saying to the developers that don't build beyond 500-meter height. So this is the top height that they are now restricting themselves to. And they can clearly see that beyond this height, there are a lot of problems. So they are restricting and uh, they have imposed this condition on the developers to not go beyond 500 meters. Anyway, so in India, we are mostly at 225 to 100-meter range as of now. But in future, who knows? This we may uh, start building even taller. And this tall building construction is the way forward because if you see, there is a lot of population that is coming to urban centers. So from rural, the population is coming more and more to the urban centers, not only in India, but also across other regions also. Uh, and cities, as you know, have limited space. So the only option is to construct vertically up, up and up. If you have heard about Manhattan, have you heard about Manhattan in New York? Hello. So Manhattan, New York, you can say can be can be said as the place where this all tall building revolution started. Let's say 100, 125 years ago. Chicago and Manhattan, New York. Yeah, these two places, I would say, are the places where historically tall buildings started getting developed more and more in the last 100, years. So what I am telling is in Manhattan, they have built so much tall buildings and they have created so much additional area out of building tall buildings that if let's say the Manhattan land area is let's say X, just to give you a perspective, if your Manhattan land area is X, if you add up the total area that has been created out of building tall buildings, it's already around 3x. Okay, this is huge. That means Manhattan has already tripled its area just by adding taller and taller buildings in its geography. It has been able to create a 3x area out of a available X area. Are you able to understand? Hello? Quick yes, no? So by building tall, by adding more and more floors over one above the other, you are able to create more area. And in urban centers where there is always a space crunch, this may only be the option that is left ahead for the humanity to construct vertically up. All right. So in India, the trend of tall buildings is only going to increase. It's not going to come down anytime soon. And in spite of the obvious importance of tall buildings, the tall building design is not as such covered in undergraduate or postgraduate studies. And therefore, the structural engineers, we have to either learn these things on the job or we may have to learn these things on our own. And many of the companies also, while they recruit these days, they ask for a relevant experience in tall buildings. So that's why we have come up with this course. I have already talked about it in the introductory session. So I'm not going to repeat it over here again. What are we going to do? Why this course? We thought we will start. I have already talked about it. So I'm quickly going ahead. And all these topics are the topics that we are going to cover. We may slightly modify or we may slightly vary the sequence of these topics, but these are the topics that we are going to cover. I have spoken about this in the introductory session, so I'm not going to repeat over here again. Okay. Yeah. So these are all the topics that we are going to cover. Very good. Now let us start with the first topic. Let us start with the first topic in our course, and that is to let's and that is to discuss a historical development, a historical perspective of these tall buildings. Let's go through the history of past, let's say around 130 years, and see how these tall buildings have been developed over this time period. Before that, anyone having any question may please ask. Anyone having any question which they may like to ask right now? Mr. Deep is asking, after analysis of building of any story, which parameter shows or define that we have to design as a concept of tall building? Eh? What does this mean? After analysis of building of any story, which parameter shows or defines that we have to? Mr. Deep is saying that when will we understand whether a building has to be designed as a tall? See, it's not about designing. As I told you, it's if you're designing a normal building, tall building, you will apply your earthquake loads on this also. You will apply your earthquake loads on this also. But as an engineer, you will begin to understand that a few things which you were doing in a regular building are not working out in a tall building. Okay. For example, a normal moment frame, a normal moment beam column moment frame, your regular G+10 building was quite okay by providing a regular beam column moment frame. Your drifts were under control. Everything was under control. But when it's a G+60 story building, a moment frame system is not working for you. That means you're not able to control the drifts, you're not able to control the deformations, the lateral acceleration is causing a problem. So then you may have to think about some other aspects, other scenarios. So that's when you'll understand that this building behavior is slightly different than a regular building behavior. Okay. Mr. Rishabh is asking, when we design tall buildings, what will be the design life, as Empire State Building, which was constructed 93 years ago, is still stable? Yeah, of course you will. If you are putting so much money, if you are putting $2-3 billion in a tall building, $2-3 billion is what? Around 23-24 thousand crore rupees. So if you're putting so much money into a structure, naturally you would not like to have it only function for 30-40 years, isn't it? Obviously, you would like that it goes on for 100-120 years at least. So design life as such, it's not mentioned anywhere, but as a designer, you can take this call that for how many years you would like your design to be, to stand. Question, are pile foundations and their interpretation from geotechnical studies in this syllabus? We will be doing raft plus pile system. Interpretation we'll briefly look into, but we have done a complete course on foundation systems. So if you want to go in depth, I will recommend you to have a look at that particular course where we have gone in depth with all the different substructural systems. Mr. Rishabh is saying, so for 120 years, we'll have to design as per the time history analysis only. No, who says that? Who says that? There is no mandate as such that if you are doing 120 years, you have to design for time history only. There is no mandate as such. Yeah. Maybe if you increase the design life, if you want to increase the design life, maybe the return periods that you consider for, let's say, wind, they may have to be taken as higher. Okay. So you may have to look at some higher return periods, maybe 120-year return period or 200-year return period. You design for that for strength. So if you are taking more design life, you have to increase the return periods for your probabilistic loads. Same goes with earthquake also. For materials, you may have to see their durability aspect very, very closely because you want your structures to perform for a very long time. So durability aspects may have to be looked into in lot more detail if you want to increase the design life of your structure. Clear? Okay, good. So let's now have a look at the historical developments of these tall buildings over the past 120, 130 years, beginning sometimes in 1890s. Okay. So in the ancient world, the tall structures that were built were only the monumental structures. What do I mean by that? So people were not living in those structures. Okay. That is what I mean by structures which are monument-like. So for example, if you look at the pyramids, or if you look at ancient temples, or if you look at Vishnu's Thumb or Qutub Minar at Delhi, or if you look at Eiffel Tower is recent, not much old, but yeah, if you look at the old wonders of the world, if you look at Statue of Liberty, all right, all these are tall buildings, but they are not buildings where people live. Are you getting my point? So those are monument-like structures. Now, what is one problem? Why building tall is a problem? Hello? Why building tall is a problem? And why living at upper spaces is a problem? Tell me. No one? Okay, we'll see. Wait. Let me go ahead. Then we'll see. Why living tall, why living at a taller height is a problem. Okay, so in the earlier world, this was the problem. No, not the problem. In the earlier sort of tall structures that you had, Mostly they were monument-like structures, not habitated or not lived by people. Now, why build tall? Mostly a tall structure is a way to satisfy the human ego. Okay. You want to show to the world that you have arrived. You can build tall structures. You want to show to the world prestige and power through building taller structures. Okay. You want to show the limits of engineering that you can reach by building tall. So mostly the tall construction started. See, in earlier 130 years ago, there was not a space problem. Okay. If you were living in Chicago or Manhattan, you had lots of empty spaces. Okay. So tall buildings were not being built because you had a problem of space, but they were being built just to show your economic and engineering capabilities. So this is how we started constructing tall. All right. Now, over the past so many hundred years, if you look at the development of tall buildings, it has mainly relied on these factors, and those factors are development of materials. Now, what I mean by material, which were the materials that were available earlier? Hello, which were the materials available earlier? So earlier you had masonry like material. It can be a stone masonry or brick masonry. What is the problem with stone or brick masonry? What is the problem with stone or brick masonry? Huge load. Yeah, you can say high self weight. High self weight is a problem. What is the other problem with masonry? Masonry can only take which type of loads? Compressive or tensile? So masonry units, unless you do not reinforce them with a secondary material, masonry can only perform well under compression. So now if you have only masonry as your building blocks, and suppose you want to create tall structures, what is the problem? If you want to create a tall structure, its base also has to be very wide. Are you getting this point? Suppose I had to create a tall structure, its base also has to be very wide. And if I am spanning some horizontal members, the distance between these vertical members also has to be very small. Yes or no? Hello. What I'm saying, if you want to build a taller structure using masonry, number one point is that because of the huge loads and because of the fact that it cannot take tensile loads as much, you have to create very wide bases for the vertical elements. For the horizontal elements, because you cannot allow much tension or much flexure in these horizontal elements, you have to also restrict their spacing, spacing between the verticals. Are you getting this point? Hello. Quick yes. So that's why if you see old structures, old temples, old constructions, you will always see very closely spaced vertical elements, closely spaced columns. You will always see that out of your plan area, 15 to 20% of your plan area is eaten up by your structural element itself, isn't it? 15% area or 20% area may be eaten up by structural element itself. So what is the problem? The sellable space goes down. Are you getting this point? If 15 or 20% is your dead space, so that means you're constructing 100 meters square and you're only able to sell 80 meters square. The rest 20 meters square is unsellable because it is being covered by structural elements. So it may not make economic sense to do that. Is it clear? Hello? Is it making? Yeah. So when it comes to material, if you do not have a material or if you have a material which can only take compression, the structural forms that you will have to create will be such that they will they will add to a very large area being eaten up by the structural system itself, and it may not make much of a sense to build tall, because more and more tall you try to go, more and more plan area is being eaten up by the structural elements. So economic sense is not, or it does not make economic sense to build tall if you only have masonry like material. But then what happened, that people started manufacturing and using cast iron in their construction. Okay, so I'm just showing you the progress, what happened. Okay, so earlier only, let's say 150 years ago, 200 years ago, you only were using masonry units, but then slowly the cast iron started. Cast iron manufacturing is a very old technique. Okay, known to India, known to Indians for many thousand years. But in Europe, this came late, and even when it came, you mainly had the cast iron. So cast iron also has this problem that, uh, of course, it has more strength than masonry, but there is still a limitation when it comes to the strength. Okay, so cast iron may still have a problem. So cast iron, and from cast iron, what got developed was wrought iron. So wrought iron, the metallurgical composition was slightly changed, which meant that it had more strength, and not only compressive strength, it also had tensile strength because of the changes in metallurgical compositions. Okay, so suddenly you had a material which has very high strength in compression and also in tension. And of course, wrought iron then gave way to steel, structural steel. So when you had wrought iron, what started happening? That suddenly you could now construct buildings of wrought iron members. Are you getting this point? Hello. That means earlier, if my plan area, if large part of my plan area was covered by masonry, I'm showing you a plan, and all these were load bearing masonry units. Now suddenly what happened, that instead of having such a large plan coverage by masonry, I could have a plan area, and only in 4-5% I could manage my structural members, because let's say I replaced my masonry structural members by steel members like this. This is the plan. So let's say this is steel columns. Suddenly what happens, as Mr. Chinmay is saying, my usable space increases. Hello, yes or no? So if you compare, if earlier case 20% was the structural, was the space eaten up by structural members, so my sellable space was only 80%. Now compare this with a system where only 3-4% is the structural system area. Coverage of structural members is only 3%, let's say. So suddenly I have a 95-96% sellable space. So suddenly I see that my project starts becoming economically viable. Is it clear what I'm trying to explain? Hello. That's all economics. At the end of the day, if your product is not sellable, it does not make any sense to make it, isn't it? So the development of tall buildings largely relies on the material and the way in which the materials were developed over the years. So you, starting with masonry, the industrial level production of cast iron started, and improvements in cast iron gave way to wrought iron, improvements in wrought iron, and you started getting steel. And with steel, USA was a big manufacturer of steel during the pre-World War era. So they had large factories which made lots and lots of steel, and these steel were being used more and more in their construction. Okay. With more development in material, if you now see, you started getting technological improvements in concrete also, isn't it? So if you see in the past 30-40 years, the development in concrete technology is tremendous. There has been a large improvement. The degree of improvement, if you see, is very, very high degree of improvement in concrete technology. Just give me 2 minutes. Yes, is my voice audible? So I was telling you earlier, uh, in the past 30, 40 years, if you see, the technological improvements in concrete have been huge. Okay. So now you have extremely high strength concrete available. You have the, let's say, 60, 70, 80, even M90, M100 strength concretes are available. You have good pumping techniques now available where you can pump concrete to greater heights. You have the self-compacting concrete available where you can use those concretes in congested zones, congested regions, sections where reinforcement is very heavily congested. So improvements in concrete technology has led to high strength concrete being available. So now you have good steel, you have got good concrete, and because you have good concrete and good steel, what has happened naturally? Tell me. If you have got good concrete and good steel, what happens? That you now try and combine them both, and now you see more and more. What do you see more and more? Hello, correct? If you start combining concrete and steel together, so now you see more and more composites being used. Not only RCC, of course, composite systems being used more and more. So you combine steel, structural steel with concrete. So these days, if you see, more and more composites are being used in the tall buildings. So what I'm saying, if you look at the development of tall buildings over the past 130 years, it started with masonry like structures, but then because of development of steel, structural steel that is, you saw more and more structures in 1930s, 1940s up till 1970s being constructed in steel, structural steel. But 1980s onwards, now these days you see more and more RCC being used in tall buildings. And over the past 15, 20 years, you now see composites being used also in tall buildings. I'll just show you a figure which is very instructive. Uh, how the trend of material consumption has changed over the years. I'll just show you a good figure for that. Just give me a minute. I'm just searching it on the internet. This is a good figure. Yeah. Let me just download this. Mm, Save. Or- Give me a minute. I'm just opening one very good image, very instructive image. Where is the image? I am opening an image which shows how the pattern of material being used in tall buildings has changed over the past years. So, what does that? Hmm. Yeah, let me just share my screen. Can you see this? Is this image visible? Yeah. So this image, what it is telling us, very interesting image. What it is telling that if you see decade wise, they have just listed down, they have sort of analyzed the materials that were used, let's say in the 100 tall stories, 100 tallest buildings of 1930. Then they have analyzed and listed down the materials that were used in the 100 tallest buildings made in the 1940s and so on. Okay. So what you can see is that in the earlier decades, around 1930s, 40s till 1980s, the the material of choice for building tall buildings was what? What was the material? It was more and more, it was structural steel. Is it clear? Hello? Quick yes, no? All right. So the choice, the material of choice was structural steel. If you see all these buildings like Empire State Building, or if you see, let's say the World Trade Center, or if you look at the John Hancock, or if you look at the Sears Towers, all these buildings that were constructed in 1970s, they were mainly till 1970s, they were mainly built in structural steel. Now, post 1970s, post 1980s, as I was explaining, that the material improvement started happening. So, concrete technology was developed a lot post 1980s. You started getting high strength concrete. You started getting high strength concrete, and therefore you see this red box is showing concrete. So you start seeing concrete being used more and more. Clear? And with concrete, if you want to get the best out of concrete and steel both, when I say steel, I am saying structural steel. When I say concrete, it is the reinforced cement concrete. I hope you get it. Okay. When I say concrete, I mean reinforced cement concrete, reinforced with reinforcement bars. When I say steel, I say only the structural steel where you use structural members, hot rolled sections for constructing tall. So now you see a trend where more and more concrete is being used post 1980s and the steel consumption is going lesser and lesser. A reason for this is also that the building tall started shifting to Asia and West Asia and Southeast Asia in the decades 1980s, 1990s, isn't it? The tall construction started shifting to countries like China or Malaysia or Taiwan or UAE, Abu Dhabi, these regions, you could see more and more tall construction happening. And over there, you have got cheap labor, isn't it? You have got cheap labor. So if you have got cheap labor available, then your concrete naturally is the material of choice. Do you get this point? Hello? If you have got cheap labor available, then naturally concrete is the material of choice. Why? Because even though structural steel is costly, why do Western countries prefer constructing in structural steel because structural steel does not require a lot of labor on site for construction. And over there, the labor is exorbitant. It is extremely expensive, unaffordable labor they have. So in the Western countries, they prefer structural steel more so because material wise it may be expensive, but the labor wise it is less intensive, and therefore it makes more economic sense to construct in structural steel. If you see the trends in Asian countries, the you get cheap labor, so concrete becomes the material of choice. Is that clear? Hello. So this trend post 1980s shifting to more and more concrete is also because the trend of constructing tall started shifting to Asia 1980s onwards, and in Asia the usually people like to prefer concrete more because of availability of cheap labor. And now what you see also, the trend increasing, this green these green values are indicating what? It is composite. So now if you have good structural steel available, if you have got good concrete available, why not combine them both? Isn't it? And when you combine them both, you get the advantages of both. You get the best of both the worlds. So you start using composites more and more. Is that clear, please? Quick yes, no? Hello? Yeah. So therefore you see use of composites increasing in the later decades. Therefore, you see the trend of composites increasing in the later decades, and all structural steel has gone almost out of fashion. All structural steel now has almost gone out of fashion. Structural steel has obvious disadvantage of fireproofing and the high cost also. And as I just explained, if you have got cheap labor availability, it does not make sense to construct tall using structural steel. So the development of tall buildings, if you look in the terms of material, I hope it's making sense that how the things developed over the past 100 years, how the choice was initially structural steel, and then later on that choice shifted to concrete more and more, and now composites. Clear? Yes. Mr. Arvind is saying the World Trade Center had structural steel core. This may be related to that incident. Which incident I didn't understand? Oh, you mean the terrorist attack? No, no. If a plane has to strike, no, no. If a plane has to strike, even if it strikes a RCC building, it's equally damaging, isn't it? You cannot design a building for plane impacts. Even if it strikes a RCC building, it's going to be equally damaging. Yeah, fireproofing, you can say there is an additional cost involved for fireproofing. But see, nobody is going to anticipate and design for a plane hitting your tall building. I mean, not even today, tall buildings are designed for plane impacts, isn't it? All right. So material, development of material, how it impacted the tall buildings, I was trying to explain you. Then another aspect due to which people started making taller and taller structures was the vertical transportation. What do I mean by vertical transportation? What is meant by vertical transportation? Hello. Vertical transportation means lifts, elevators. Very good. Elevators. Okay. Now, I don't know your fitness levels, the participants who are attending, but I think even if you have to climb up 8 or 9 stories these days, you may be using elevators to go up and down, isn't it? You may be using elevators to go up and down even in a 8, 9 story building. So imagine a 100-story building, and if you do not have elevators, it 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 is almost practically impossible that a person will be able to climb to that height. Are you getting this point? Hello. If you have to reach 100 stories and if you have to climb stairs, it's practically impossible that you will be able to climb all those levels and reach to the top, isn't it? So if you don't have vertical transportation system available, the taller, the higher levels, will they be sellable or not sellable? If you, the taller, higher levels, will it make sense to buy them? Will it be, it will not be sellable enough, isn't it? It will not be sellable enough. So the development of vertical transportation systems, mainly in the US, starting in 1870s, led to steam elevators being used. So earlier the elevators were powered by steam. In 1870s, you might have heard about the Otis elevators. Otis. So this was name of a person who started using steam elevators, who started fitting steam elevators in earlier buildings in New York and Chicago. Have you heard about Otis? They are still one of the world's leading elevator suppliers, manufacturers. Otis. No one has heard? Arre, what are you saying? If you go to some buildings right now, also in on lifts, you see either you see a Kone or Otis or Schindler or which other companies you see for elevators? Schindler you see, Kone you see, Otis you see. Any other company that comes to mind? Otis, Schindler. I can think of these four or five companies. Okay, so this Otis, this is name of a person, surname of a person. I am not able to recall his full name, but they started with the steam elevators back in 1870s, and by 1890s, Otis had started manufacturing electrical geared operated elevators. Okay, so once you now had this technology of elevator by which you could transport people up and down. Now suddenly the topper levels started becoming more and more sellable. Yes or no? Now height was no longer a restriction for you. You could add stories on top of other. You could keep on adding stories one over other because you could reach those higher heights by the help of elevators, isn't it? So the development of elevator, the development of vertical transportation was a very, very important step in the overall development of tall buildings. I hope you are able to appreciate the importance of vertical transportation. Yeah, it's quite important. So these developments led to people and developers getting this confidence that yes, even the higher floors are sellable. Because see, if you are at higher level, you have the obvious advantages of views, isn't it? You have the obvious advantages of view. And if you are able to reach those higher levels comfortably in an elevator, then the advantages of views can be sold at a premium. Okay, so you can sell your taller building at a, sorry, you can sell your upper stories for a premium. Yeah, but you have to first be able to reach over there. So for that, vertical transportation developments played an important role in the development of tall buildings. And if you have heard about the super tall buildings that you have like Burj Khalifa or the Empire State or even the World Trade Centers or even the Willis Towers, all of these have uh, high speed elevators. All of these have extremely high speed elevators these days. Okay. So you can reach to the top of Burj Khalifa, 826-meter tall, or even 600, 500-meter tall buildings. You can reach in 15-20 seconds, isn't it? Extremely high-speed elevators these days are used. So vertical transportation has ensured that you can go tall and tall without having to worry about how to reach over there. Once in a while, all of you, if you are living in buildings, if your offices are in buildings, once in a while, you should try to climb the stairs also. Why? Because let's say if tomorrow there is an electrical power breakdown, at least you should have that fitness level that you can climb up or climb down from that particular story. How many of you work in offices, let's say 7, 8 stories up? No one? Right. No one works in the offices? Oh, 65 stories. Mr. Mohammed is working in 65. Where do you work? Oh, in Dubai. Okay. So he is working in an office 65 story tall. Are you able to climb on your own stairs? No. You should practice once in a week. Uh, Maybe you can start with, let's say, climbing 10 stories and then taking a break. Then next week, maybe you can try to go 12, 13 stories. And maybe in 5, 6 months, on a weekend, maybe as an exercise, you can try and climb up all the 65 stories on your own. Very good, very interesting. Mr. Chinmay works, he worked at a site which was G plus 15 and he used the stairs to reach. Very nice. Very good. Okay. So vertical transportation development led to a complete reimagining of the tall buildings. Then comes the power of computing or the analysis techniques that were developed. Now, Empire State Building, when was it made? Why do I keep going to Empire State Building? Because it was one of the tallest buildings for almost 30, 40 years in the world. So, when was the Empire State Building made? So, Empire State Building was made sometimes in 1931, maybe. Okay. So, 1930. Yeah. So, at that time, forget about computers. You even didn't have any proper analysis method available. You only had the Hardy-Cross method. Hardy-Cross method is a precursor or a pre-method to the moment distribution. Have you heard about Hardy-Cross? He was an engineer, by the way. Hardy-Cross was an engineer and he wrote a paper about the moment distribution in redundant frames, something like that. That paper is still available on the internet. You can have a look at it. So he wrote a paper. He was a practicing engineer. He wrote about the analysis of redundant frames, something like that. So in 1930s, only this Hardy-Cross method was available for analysis for calculating moments in a redundant frame. So obviously, because of the limited analysis capabilities, you could not do a lot of analysis because there's a limit to manual calculations that you can perform. Okay. So the systems had to be simple. The shapes had to be simple. The structural system had to be simple because you could not analyze complicated systems. Are you getting this point? So in 1960s, 1970s, because of computing, because computers started happening in USA, because you started getting increased computing power, what happened? That now you could come up with taller shapes, not taller shapes, you could come up with more uh, non-regular, non-linear shapes earlier, which you could not analyze them. But now because of improved irregular shapes, and now because of improved computing power, it was possible for people to analyze them to find the moment, shears, etc., and then design them. See, designing is simple if you are able to analyze it properly. You get it? If you are able to analyze, design is not a problem. And these days, because of computers, we are able to analyze almost anything under the sun, isn't it? Because of supercomputing powers that we have. Even our laptops are supercomputers. If you compare it with the computing power you had in 1970s, even our laptop or a home desktop is a supercomputer if you compare it with the capability of 1970. So with vastly improved computing techniques, you can analyze almost anything that you can think of. And because you can analyze it, you can design it. And because you can design it, you can construct it as well. Are you getting this? So if you have seen, I don't know if you have seen that Bird's Nest Stadium in Beijing, which was built for the Olympics, Beijing Olympics 2008. Now, if that type of sort of structural system, you could not do it manual calculations. You're getting this point? You could not do manual calculations for such a complex system. But because you had improved analysis techniques, you were able to conceive that, conceptualize it, you were able to analyze it, and then you were able to design it as well. So improved computing powers, improved analysis techniques meant that you could construct taller and taller. Okay. Mr. Mehul is providing this information that the design was done by Arup and hollow sections were, yeah, all those sections are hollow sections and intertwining members like a nest, and extremely amazing structure. I mean, amazing. It was done, it was analyzed using SAP 2000, I think. It was analyzed using SAP 2000 software. Yeah. Okay, so improved computing powers meant that you could start making more irregular shapes. You could start coming up with complex systems, and you could analyze them and design them as well. So this is another aspect which you see, which led to development of tall buildings. Then newer structural systems. So if you see the earlier systems, they were mainly your moment frames. Okay. If you look at the Empire State Building also, they were normal moment frame buildings. But then, no, Empire State Building has a, yeah, I think Empire State Building is a moment frame system. But because of development of newer and newer systems, which I will be talking more about later on, so by practicing engineers started developing newer and newer structural systems which could carry your lateral loads more efficiently and in a better way. Because of structural efficiency that was possible because of the newer systems, you could think of going taller and taller and yet make economic sense. Okay. So again and again, I'm repeating that if it does not make economic sense, there's no point in constructing a tall structure. Okay. So because of development of newer structural systems, you could you could go tall and yet remain structurally efficient, thereby providing economic solutions for greater, taller heights. So development of newer structural systems is an important point, is an important aspect why we could go tall and why we continue to go taller and taller. Another reason why you could go taller and taller was the improvement in our understanding about the wind loads, wind engineering. I am focusing more on wind, less on seismic. There is a reason which I will tell you later. But improvements and developments in wind engineering, mainly by uh, a person named as Davenport, if you have heard his name. So he was a professor, I think. Yeah, he was a professor at a University of Ontario, Canada, and their team did a lot of work on this dynamic effects of wind load, vortex shedding, dynamic effects of wind load, gusting, gust effects, and then they were the ones to come up with the numerical calculation So for example, the gust factor formula that we have, even in the Indian code, have you seen the gust factor formula that we have? So even that formula is derived on the work done by Davenport sometimes in 1940s. Okay. So improvement in our understanding about wind, development of wind tunnel testings led to led to systems and structures which could be made taller and which could be economically analyzed and designed because of our improvement in understanding of the effect of wind, its behavior, and also because of the development of wind tunnels. Okay, so now almost all tall buildings essentially have to be tested in an actual wind tunnel, and only after it passes wind tunnel test, you, you take the forces and you take the moments and you take the analysis outputs from wind tunnel, and then you use it for your analysis design. And from the wind tunnel experiments, you're also able to change the shapes, change the system, change the plan, change the planning of your building in order to make it more efficient against wind loads. So wind tunnel testing, improvements in wind tunnel testing, improvements in the understanding over the past 50-60 years about the effect of wind has led to development of taller and taller buildings. Is that clear? Yeah, RWDI are experts. I will recommend you to go to their website, RWDI, as Mr. Mehul is saying, and visit their website and look at their case studies that they have done. Okay. See, a good wind tunnel engineer is not the one who will just carry out the wind tunnel test. Anyone can do the wind tunnel test. A good wind engineer is one who can suggest the shapes, who can suggest the changes, who can suggest better forms for your tall building in order to minimize the effects of wind loads. You understand? Those are considered as good wind engineers who can give these suggestions to architects and structural engineers. So wind tunnel testing anyone can do, but a person who can give suggestions, who can give their inputs, is the person who is of great value. For example, if you have looked at the Taipei 101 plan, earlier it was a rectangular plan, square plan. I am talking about the Taipei 101 building. I'll show you the images later on, but I hope you have heard about Taipei 101. So the big, after wind tunnel testing, it came out it came out that providing a notch like this at corners, double notch. So instead of a square plan, providing a double notch at corners will help to mitigate the effects of wind in a much better way. So after the wind tunnel testing, the architects and the structural engineer decided to change their plan shape from a square shape to this double notch shape at the corners, and by this they were able to save a lot on the wind forces that were being experienced by the structure. Do you get it? So a good wind engineer will always suggest the way in which the wind loads can be mitigated, and good plan shapes, good plan sizes, good geometries that you would like to provide in order to minimize the effects of wind. So developments in wind engineering over the past 50-60 years has also led to has also enabled us to has also enabled us to construct tall and taller. Advances in geotech engineering over the past 100 years, mainly in the field of soft soils, moderate soils, poor soils, and mainly in the raft and pile systems, mainly in deep foundations, has also helped us in constructing taller structures and being able to support them adequately. Clear? So because you are able to have a efficient substructural system, therefore you would like to go taller and taller. And these days, the thing which is being developed and which will be developed in years to come is the soil structure interaction also. There are a lot of studies going on about the soil structure interaction and how efficiently you can model the soil as a part of your structure, and how you can look at the combined effect of soil and structure both, and how that can be efficiently used in making the design more economic. That also is the thing which is being done these days. So the advances in geotech engineering, how you can support a substructural system, especially in the poor or moderate soils, and development in geotech engineering has led us to construct tall and taller. So these are, yeah, economical structural systems I already talked about. So I would say these are the main factors which have led to development of tall buildings. So materials, uh, vertical transportation, computing power and analysis techniques, newer structural systems, development in wind, and as Mr. Mehul is adding, I should have added, yeah, it's an important point that I should have added. Improvement in the construction techniques also, yes, advances and improvement in construction techniques, construction machineries. Yes, I should have added it. That is also an important point, because you may analyze and design and come up with a 1000-meter tall building, but if you don't have the adequate construction techniques available, if you don't have the cranes and the systems available, if you don't have the uh, capability of constructing these heights, then I mean, all your analysis and design is waste. So improvements and advances in construction machinery, the slip form techniques that you have now, the aluminum formwork systems that you have now, uh, the the pumping techniques that you have, you are able to pump concrete 800 meters into the sky. So all these techniques and advances are important for allowing us to go taller and taller. So yes, I should add this point as Mr. Mehul rightly put forth. Yes. So these are the factors which have led to, if you see, if these are the factors that have led us to constructing taller and taller structures over the past so many years. Okay. So I think I'll stop over here. Yeah, I'll stop over here, and tomorrow we will just have a look at the different buildings that have been constructed. Some notable buildings I would like to show you that have been constructed over the past 100 years, and we will just have a discussion regarding them. So I stop over here right now. This session will be uploaded on the portal by afternoon. So all of you can go to the portal where you have already been added, the details for which have already been shared, and you can go and have a look at them. And you can watch the session as per your own convenience in case you are unable to attend the live session. If you want to do both, you are free to do both. That is, if you want to attend live as well, if you want to watch it on the portal also, you can do that also. All the options are available. You can avail whatever suits you. Okay. So I think that's all for today. Tomorrow we'll just have a look at some notable buildings, uh, notable tall structures that have been constructed. Yeah, Mr. Mehul also said that advances in construction technique and advancements in the geotechnical machinery also. Very right. So if you are able to now dig 50, 60 meters into the earth for piling, if you are able to reach hard strata, however deep it may be, So that is possible only because of the newer construction machines that you have, and that has allowed you to construct taller and taller buildings and not worry about the substructure that much, because you can reach deep into the earth for piling and for deep foundations. Very right. Yes. So I think I stop. That's all for today. We'll continue with this tomorrow also. Thank you. Bye bye.